Question 16. Figure 6 shows a sketch of the curve C with parametric equations. X is equal to 2 tan t plus 1, y is equal to 2 sec squared t plus 3, where t is between minus pi by 4 and pi by 3. The line L is the normal to C at the point P, where t is pi over 4. Part A, using parametric differentiation, show that an equation for L is y is equal to negative a half x plus 17 over 2. Well, if we're going to do some differentiation here to show this line equation, the link is going to be in the gradient. So I know that the gradient of a line which is normal to the curve at point P is going to be the negative reciprocal of the gradient of the tangent at point P. And so I need to find this curve C. I need the gradient function dy by dx. Now, since x and y are in terms of t, I need to use my chain rule. So I know that dy by dx is equal to dy by dt multiplied by dt by dx. And so I have y is equal to 2 sec squared t plus 3. Differentiating gives me that 4 sec multiplied by the derivative of sec, which is sec tan. So I have 4 sec squared tan t. 3 being a constant differentiates to 0. I have my x is 2 tan t plus 1. Tan differentiates to sec squared. Again, the 1 is constant, differentiates to 0. I'm going to go one step further here. This is dx by dt. If I look back to my chain rule, I want dt by dx. So dt by dx is 1 over 2 sec squared t. Now I have what I need to use my chain rule. So dy by dx is equal to dy by dt multiplied by dt by dx. So 4 sec squared t tan t over 2 sec squared t. I can see the sec squareds cancel, and 4 divided by 2 is 2. So this gives me 2 tan t. Now I want to use this to find the gradient of the tangent at the point P. At the point P, I'm told t is equal to pi over 4. And so my dy by dx is going to be 2 tan lots of pi by 4. I can also use this value to find my x and y coordinates. My x will be 2 lots of tan pi by 4 plus 1, and my y will be 2 sec squared pi by 4 plus 3. Evaluating each of these on my calculator gives me that dy by dx is equal to 2, and the coordinate at that point is 3, 7. Since L is the normal at P, the gradient of L is the negative reciprocal of this tangent gradient 2. So the gradient of L is negative a half, which is good because that's what we're looking to hopefully show. So we're now at the point where we know the gradient of the line L is negative a half, and we know the coordinates of the point P are 3, 7. I can use my standard equation of a straight line formula now. So y minus y1, 7, is equal to negative a half x minus 3. Expanding the bracket on the right hand side here gives me y minus 7 is equal to negative a half x plus 3 over 2. Adding 7 to the right hand side gives me that y is equal to negative a half x plus 17 over 2, which is what I wanted to show. Perfect. I now want to show that all points on C satisfy the equation y is equal to a half of x minus 1 all squared plus 5. Now this is quite a strange question to think about. We've got x is equal to 2 tan t plus 1, and we know that y is equal to 2 sec squared t plus 3. So what I'm looking for is an equation that we're aware of which link tan and sec. Now, we should all remember and have fresh in our memory sine squared plus cos squared is equal to 1. Now, this is the one I always remember, and with this one, I can derive further trig identities. In this case, if I divide every term by cos squared, then sine squared over cos squared is tan squared, cos squared over cos squared is 1, and 1 over cos squared is sec squared. And so this identity here, tan squared plus 1 is equal to sec squared, is what we're going to use to equate our x and y. And so I would like to write tan t in terms of x and sec squared t in terms of y. Taking away 1 and dividing by 2 gives me that tan t is equal to x minus 1 over 2. Taking away 3 and dividing by 2 gives me that sec squared t is equal to y minus 3 over 2. And now I can substitute these values for sec squared and tan into this identity. Tan squared is going to be my x minus 1 over 2 all squared, plus 1 is equal to sec squared theta, which is my y minus 3 over 2, squaring this bracket here, so x minus 1 all squared on the numerator, 2 squared is 4 on the denominator. Can now multiply through by 2 to give me x minus 1 squared over 2 plus 2 is equal to y minus 3. Adding 3 to the left hand side, we can switch this round here so that y is equal to a half x minus 1 squared plus 5. Again, what I wanted to show. The straight line with equation y is equal to negative half x plus k, where k is a constant, intersects C at two distinct points. Find the range of possible values for k. So if we imagine this line L, as we already know this line to have a gradient of negative a half, when we have a line that cuts a curve at 2 points, we want to be able to form a quadratic where the discriminant has a value greater than or equal to 0 in order for it to intercept at 2 points. And so in order to find that, we're going to put the equation of our line L, negative a half x plus k, equal to the equation of our curve, half x minus 1 squared plus 5. Expanding the brackets on the left hand side, we've got a half of x squared minus 2x plus 1 plus 5 is equal to a negative half x plus k. Multiplying everything by 2 gives me my x squared minus 2x plus 1 plus 10 is equal to negative x plus 2k. Now arranging to give me a quadratic here, I've got x squared minus x plus 11 minus 2k is equal to 0. So the discriminant here, b squared, is 1 minus 4ac. So 4 lots of 11 minus 2k, I need to be greater than 0 in order for it to have two real values. Expanding the brackets gives me 1 minus 44 plus 8k is greater than 0. Adding 44, subtracting 1 and dividing by 8 means that k must be greater than 43/8. And so that is the point here. That's the minimum point that L can get to. Now if we imagine L moving up this graph, there is a point here where the curve no longer exists, and so it would only be crossing one point. So I need the value of k at this point to be the upper bound. And so my max value here is when t is equal to negative pi by 4. When t is equal to negative pi by 4, that is when x is equal to negative 1. Evaluating 2 tan negative pi by 4 plus 1 on your calculator. And so substituting x is equal to minus 1 into our simultaneous equations gives us a half of minus 2 all squared plus 5 is equal to a half plus k. This gives us 7. So 4 divided by 2 is 2 plus 5 is 7 is equal to a half plus k. Therefore, the greatest value that this can take is k equal to 13/2. Therefore, k must be greater than 43 divided by 8 and less than or equal to 13/2.